Okay, all right, time to get started. So we finished 3.3 last time. We're going to move into 3.4. Oh, of course, reminder, attendance quiz, attendance code, all that. Remember, what's the phrase? Anyway, clock's ticking. So make sure to get that in. Okay. Right, so new section. So we're going to talk about some kind of weird stuff today, at least for the first part of today. Hopefully we'll be able to get into the next chapter also today. But so there's a bunch of ideas that come up in chapters 6 and 7. Y'all heard me make allusions to that here and there so far this course. But it's a lot to digest. And so one of the clever ideas that pros and cons, but I think in the net, I think I support this idea, is to introduce some of those ideas early when it's really kind of mathematically too early. We don't really have the tools to actually be able to justify and make sense out of the stuff that I'm about to show you. But getting those images and those ideas percolating in your minds, starting to sink in, will pay off when we actually get to talking about these things later on. So that's what 3.4 is. It's a bunch of kind of ideas that'll make more sense later. Okay, so the first thing is just a notational point. Let's see here. So y'all remember gradient, of course, no big deal. And the idea is to separate out this operator. So an operator is something that does stuff to a function. Basic way to think about it. So here we have an operator. This is a vector of partial derivative operators. And if you apply that to some function f, right, then notice what you get is exactly that. Right? So the idea is that we can think of del as an independent, separate thing. It's weird, right? We normally think of the gradient, del f, as being a thing. Now we're going to talk about del by itself as a thing, right? And so this is, so it's called the del operator. And, we write it as a vector. Things that we're going to do with it will treat it like a vector, even though, of course, the coordinates are not numbers and it doesn't actually point in a direction, yada, yada, yada. Okay. All right. Now let's see here. What time? Okay. All right. I'll tell you what. I'm going to pause the lecture here for just a minute, and then we'll pick it back up momentarily. Okay. And we're back. Okay. So we talked about this del operator. Okay. So what are we going to do with this del operator? Here's where things are going to get weird, as if that wasn't weird already. We're going to take this vaguely vector-like thing, the del operator. I'm going to call it a vector, right? It's not a geometric vector, but it algebraically behaves like a vector. And we're going to do a dot product with a vector field, which of course is also structurally a vector, right? And you'll notice that, I don't know if I can get this to... There's the coordinates, if you will, of the del operator. Here are the coordinates, literally, of the vector field. And this is what a dot product looks like, right? You pairwise apply and add. I mean, multiply, but, interpret as the kind of the notation suggests, right? And this is what naturally you would expect to write down. And it turns out, again, hand waving, massive hand waving, and we'll be able to justify this much better when we get to chapters 6 and 7. Turns out this is actually a very natural and meaningful and important thing. So, in particular, it's called divergence of a vector field. Now, why the divergence does what I'm about to claim it does, yeah, that's a long discussion. We don't have the tools for that yet. I'm just going to make some assertions about what divergence does. And I'm going to hope that y'all are willing to believe me, at least in the short term, and then I'll give you more thorough fleshing out later on. What I claim to the, if you're willing to believe me, that what divergence does is it measures how much the fluid is flowing away from where you've computed divergence. That's just kind of how it works. Okay, so here is a example. Here we have a vector field. That's what that vector field looks like. By the way, there's going to be a bunch of vector fields I'm going to draw pictures of. In all cases, I'm going to leave it to y'all to think through why is it that that's what this vector field looks like. You want to make sure that you can actually do that. So think through how would you break down this formula for this vector field and produce this picture. In this particular case, you might notice this has got a lot in common with one that we did last time. A little bit different, 3-dimensional instead of 2-dimensional, but very, very similar. So anyway, make sure that you can produce all these pictures. Any of them that you have trouble with, any that you can't figure out how to get started or can't come up with a different answer that doesn't look like what I've drawn, come talk to me. I'll be happy to walk you through it and figure out what the problem is. Okay, so we're going to look at the origin, and we're going to compute divergence, which, yada, yada, yada. It's just a calculation plugging straight into the formula. Make sure you can do that. That's another, just plugging in. Y'all don't need my help for that. So make sure that you can see the mechanics of how to plug in. And what we get is that the divergence is positive. Right? So now let's look at this picture and let's think about what we've computed, and let's think about what the claim was that I made about what divergence looks like. It says here, the assertion that I've made is that this is a measurement of the extent to which the fluid is flowing away from where you've measured the divergence. And I'm going to call this a massive success. Right? The divergence was computed positive. This interpretation would then say that this fluid is to a positive extent flowing away from where I've computed, namely the origin. And check it out. Sure enough, the fluid is very clearly flowing away from the origin. What do you think? Everybody buy it? Okay. Now this is just an example. This doesn't prove anything. Right? But so my goal with this example is not to prove anything and not to persuade you. My goal is to hopefully maybe give you some idea of what I meant by this language, and maybe even to a slight extent persuade you that this is not an outrageous suggestion, and at least it tracks with this one example, etc. Okay. All right. Now, I'm going to spend a moment talking about something that was very confusing to me when I was y'all's age. And I'm going to try to spare you all of that confusion. So what is divergence physically? Okay, well, it depends, as it turns out, on how you interpret this picture. What is this fluid? How does that fluid work? And then you could come up with an answer. So I'm going to give you two different takes on this. One is metaphor. Imagine that the origin is kind of where the top of a palm tree is. So tall, but it's got a small, sort of top to it. And there's a bunch of birds in the tree. I like to think of birds as a fluid. We talked about that last time. And somebody says boo, and the birds get scared, and they fly off in all different directions, right? So it kind of maybe sort of would look kind of like this, right? Okay. So if that's the case, and if we then think about what's happening to however many birds there are in that region right there, right? Where the tree was. What's happening to the number of birds in the tree? Well, there were a lot of birds in the tree, and then they started flying away. And what happens when a bunch of birds start flying away? When you have less birds remaining in the tree, right? So this is a first take on how to interpret positive divergence in that metaphor of birds and such. We're losing birds, where the bird density is going down. Right? Reasonable take? Okay. All right, now here's a completely different interpretation. Completely different physical scenario. And the point is, it's a physically different, qualitatively different physical scenario. Forget about the birds. Now pretend that this is a light bulb. Light bulbs generate a fluid. They create a bunch of these little particles called photons that kind of fly outward, but all kind of generally in the same direction. Also, kind of a fluid. Okay. If this is a picture of, by the way, the vector field isn't the right vector field for this, but details. Let's not worry about that. When I turn the light bulb on, am I losing photons? Is my photon density decreasing? Not at all. That's not how light bulbs work. Light bulbs are not little storage, little reservoirs of photons. And when a light bulb burns out, it's not because it ran out of photons. This is not at all how it works, right? It's literally generating photons. There's always the same number of photons in a light bulb. However many haven't flown out yet. It's always the same, right? So you're not losing, in this case, again, positive divergence. You're not losing photon density. You are creating the fluid. So now I think it's reasonable. You look at this picture, and if I were to say, yeah, this is what it looks like when you create fluid. If you're just generating fluid, then that fluid will just kind of flow outward. Also reasonable. Right? So what we have is two qualitatively different takes on what this might mean physically, because we're looking at different physical scenarios. Now, again, I say this is a point of confusion for me when I was young. Nobody ever sat me down and pointed out, hey, there really are different physical scenarios, and you have to interpret accordingly to the physical scenario. And so I was kind of, again, when I was y'all's age, I would interpret based on whatever occurred to me first. I would look at the picture. I wouldn't think about the physical scenario. I would just look at the picture and think, well, this is what I think that means. And I would basically randomly pick one of these. And that doesn't make any sense at all. Right? So you have to tailor your interpretation to the physical scenario. And that's something to keep in mind. By the way, we're going to revisit this question again when we get into Chapter 7. Frankly, it's worse than what I've described here. It's not just that there are these two different interpretations. It's that there is a kind of a continuum with those as the extremes of interpretations depending on the physical scenario. And so there's a lot to say about that, and that's another thing that we don't really have the tools for just yet. All right. Okay, another example, and this is just, again, doesn't prove anything, but it kind of tracks and somewhat satisfying. So here's a vector field. Again, make sure you're comfortable with how to persuade yourself of that. Let's consider some point, wherever, doesn't matter in this case, and let's compute the divergence. And the divergence you can compute ends up being 0. I claim that makes sense here. Let's think about why. There's a temptation to say, wait a minute, I see unambiguously there's a bunch of fluid flowing outward from that region. But here's the thing, you also have a bunch of fluid flowing into that region. And if you think about it, flowing into is the negative of flowing out of. So you can think of this as simultaneously there being sort of a positive contribution to divergence and a negative contribution to divergence, and they cancel. And 0 actually kind of makes sense if you think about it that way. So again, I'm going to say this kind of tracks, right? This is, that's consistent with what I had claimed. Doesn't prove anything. Hopefully it makes it a little bit more believable. Okay. How we doing? Everybody all right? Okay. Here's another weird new operator that we're going to define that we don't have the tools to make sense out of just yet. So I'm going to make some claims and hope you believe me, and hope those ideas, again, will have a chance to sort of settle over time. So if you take that same del operator, wrong tool, same del operator, and this time we're going to do a cross product, not a dot product. Remember, the way we do cross product is like this. You put the standard basis vectors across the top, and then the first vector goes in the first remaining row, and then the second vector, the vector field in this case, goes in the second remaining, aka the last row. So that's just the formula for cross product. Now, we complained when we wrote down the formula for cross product in the first place that it was a bunch of symbolic nonsense. This is even worse symbolic nonsense, because not only is the top row not scalars, aren't they supposed to be scalars? That doesn't seem right. Now the second row is also not scalars, right? That they're differential operators. They're arguably even weirder than what's in the top row. So again, sure, right? But symbolically, just compute as the notation lays on the page, and this computes what we mean when we say curl. And you could write out the explicit formula, but frankly, this is the easiest way to remember the formula for curl. So in particular, you compute this determinant by going across the top row. You start with that. You look at the corresponding submatrix. We would then take the y partial of F3 and subtract the z partial of F2. And that will give you the coefficient of E1, namely that'll give you the first coordinate of your curl vector. So again, it's kind of like computing determinant, it's just that now they're different kinds of objects. Okay, again, seemingly pulled out of nowhere. Again, we don't have the tools to make sense out of this yet. Again, I'm going to make an assertion. And the assertion is this right here. This thing called curl is a way of getting our hands on the question of how is a fluid, I'm going to use the term circulating. And I have to be careful about the terminology here. Circulation is a precise, specific mathematical construction that we haven't talked about yet, right? So this is not really sufficient for me to describe what I'm really describing. The way you should think about it right now is it's like the fluid has a rotational element to it. And an easy example is, here's an easy one, hurricane, right? The air is circulating, right? Tornadoes, even more so, the air is going around. There's a rotational, you take a hot air balloon and you toss it into a tornado, it's going to rotate quite a bit, isn't it? Does that make sense to everybody? Okay. All right. So let's get our hands dirty. Let's see one. Now, vector field, I claim it looks like this. Again, make sure you can figure that out. Let me give you a quick hint on this one. Notice the X and Y parts look a lot like a vector field we've already studied. Right? This is what I like to call the stirred pot. Right? You look down on a stirred pot and you stir it counterclockwise. The water will be doing what that describes. And then you just notice that this vector field, and nothing's happening in the z direction. So all the field vectors are horizontal. Notice there's no z dependence. So it's just kind of boring in the z direction. And with that in mind, I claim this is hopefully something you can sell yourself. Again, come talk to me if you have questions. Okay, so we compute the curl. Here's our formula for curl. Plug and chug. Good exercise, by the way. Make sure you can do this. And the curl is 0, 0, 2. Now, a couple of weird things I'll point out. First of all, that's a vector, not a scalar. What's the meaning of this being a vector? Well, that vector indicates two things. The magnitude is, in some sense, that again, we can't really make precise right now, and let me not go down that hole. But in some sense, it's a measurement of how much of a rotation is happening. And the direction is telling you the axis that it's rotating around. So this fluid is rotating around the z-axis, which again, from the picture, you can see makes sense. Is that cool? Everybody on board? The other little detail, and again, we're going to have better tools for making sense out of the following very soon, but there is a right-hand rule of sorts. So the curl being this vector. Right hand, thumb in the direction that the curl points. Notice that my fingers of my right hand are pointing a particular direction around my thumb. And notice the fluid is, in fact, kind of rotating in that direction around the z-axis. How we doing? Is that satisfying? Okay, yeah. Okay. All right. Okay. Couple more examples. This next one's quickie. It's not that interesting, but vector field, picture, compute the curl. One of the purple. You compute the curl, you get 0. 0 suggests there's no rotation. You look at the vector field. Would anybody believe me if I said there's no rotation in this vector field? I mean, I think it's pretty believable, right? So, boring. Okay. The next example is tricky. The next example is another subtlety that I was confused about when I was y'all's age, and I've seen many students get confused on this same point. This next example is a clarification of how not to interpret this example. Let me first give you the wrong interpretation of this example. The wrong interpretation is, yeah, check it out. I can look at this flow line. That flow line is literally curving around the z-axis. This is the wrong interpretation. Let me put a big X here. That's the wrong take. This term that we use here, circulation, again, I haven't been able to give you a definition of this yet. Right? So it's no one's fault that you would interpret this what it turns out to be the wrong way, because I haven't given you a definition. Importantly, circulation is not about flow lines. It's just not. This example is tempting because I can see the flow lines practically, right? You connect the dots. It really feels like the flow lines are doing what it's supposed to be doing. But in fact, curl is not about flow lines. Here's what it's about. Curl is about if you were to put a small but not zero size, just a small floating object in that fluid, in what way would that floating object start to spin or rotate? It's about the object in the fluid. It's not about flow lines of the fluid. Okay, so now, again, in this case, I think you would believe me if I said, look, yeah, you put this balloon or whatever right here, the balloon is going to start rotating exactly the way the curl suggests it should, and same conclusion for this example. Maybe a little harder to visualize, but same conclusion. Is everybody with me? I claim this is the take we have to use to make sense out of the next example here. So you look at this example, and unimpressive to start. Easy formula. There's the picture again. Think through how this is the picture. Make sure you can make sense out of this. Looking at the picture, kind of feels like the flow lines are all straight lines. And if the flow lines are all straight lines, again, if you have this wrong take on what curl is, you might make the mistake of thinking, oh, I would expect the curl to be 0. Again, wrong take. Let's play it the other way. Here's my floating balloon. What does this fluid do to that floating balloon? Well, it's going to kind of push it that way on that side, but it's going to push it this way on that side. The fluid is going to make this balloon go around what you might call clockwise. Right? Clockwise as seen from above. Right? Flow lines are all straight lines. But the balloon is going to rotate. Does everybody buy it, what my assertion is? So this balloon is going to rotate, right? And then you do the computation, and the curl is consistent with that, right? So you compute. The curl is a vector that points downward. And again, right-hand rule, thumb in the direction of the curl. Look at my fingers of my right hand going as seen from above anyway. Again, clockwise, just like the balloon would be rotating. Is everybody happy? Okay, so watch out for this flow lines. Interpretation's the wrong word. Landmine. It nonsense. It's not about curl. Is not about flow lines. Okay. All right. There's a two-dimensional curl. By the way, just to be clear, I hope it was. Yeah, I did write it down. This formula that we have right here is specifically for 3 dimensions. There is also a two-dimensional curl. Here it is. Two-dimensional curl is defined by this formula right there. And now this formula, I'm going to say it's not analogous exactly to the previous formula. It smacks of the previous formula. It's got a determinant, kind of one of these fishy-looking determinants. True, but there is no standard basis vectors in there. It's not analogous. Importantly different. That said, it is something that we can recognize, and y'all may remember the wedge product. We talked about wedge products very briefly back in section 1.4, I guess it was. And wedge product has certain things in common with cross product, and it has certain things in common with determinant. It's its own little weird little thing, but this is exactly what we need here. Del F, and that's what a wedge product is. Okay, so it's a very similar idea. Again, it represents how the fluid is circulating. Again, I haven't told you what that means quite yet. Again, the best way to think about it is imagine something floating in that fluid, and how does it rotate, and which way. Okay. Everybody okay? All right. Okay, so now even weirder, creepier, even harder to justify. But again, just planting some thoughts. Right? This is just, I want this to percolate while we do other things before we get to chapter 6 and 7. Turns out, for very hard to see reasons, it makes loads of sense to compose the gradient operator with the curl operator with the divergence operator, specifically in that order. Not just because the Legos have to fit together, right? I mean, gradient takes a function and produces a vector field. Vector fields are exactly what you need to take the curl up, right? The fact that it fits together there, it fits together here, again, the pieces, Legos and all that, yeah, that's nice and all, but that's not the point. There's much, much more deep and sophisticated reasons why we compose exactly these operators in exactly this order. In fact, ultimately, deep down, the reasons why we would do this was not really understood particularly well for 100 years or so. Right? This is very, very... Gauss never figured this out. There's one for you, right? Gauss is pretty smart. If Gauss can't figure it out, it's a hard problem. But it turns out that there's excellent reasons to do this. Patterns start to show up. Analogies start to make sense. Powerful tools come about when you compose them in this order. Now I'm going to show you a couple of these patterns just to try to sell you on it. The first one, and I'm going to phrase this in a way that I find satisfying. All lifetimes are 2. I'm going to tell you what I mean by that. But just to get the ball rolling, let me just point out, if you have a function, right, you can take the gradient of that multivariable function. That will give you a vector field, as we discussed last time. That vector field, you can take the curl of, and when you do, you will get 0. And this is what I'm going to call a lifetime. The first part of which I'll observe 0. I mean, look, it's just a metaphor, right? So don't overanalyze this. I'm going to think of 0 as being death, nothingness, if you will. Again, don't overinterpret. Tracks with the idea that, for example, if you take nothing and you take its divergent, still nothing, right? So it's got that permanence, kind of like death, if you will. Again, it's just a metaphor. Okay, so this is my first example of a lifetime being 2, and in fact, notice that's what this theorem says right here, that the curl of a gradient will always be 0. So you can think of that as a formula to memorize. The problem with memorizing it as a formula is that you'll be like, okay, wait a minute, so is it the curl of the gradient, or is it the gradient of the curl? Wait, that doesn't make sense. Wait, is it the divergence of the gradient? Or, oh gosh, and there's so many different ways that you might misremember the formula, right? But if you keep these operators strictly in this order, the little diagram does some of that bookkeeping for you. And in particular, this lifetime is 2, that means that theorem holds. And likewise, if you have a vector field, you take the curl, you get a new vector field, and then you take the divergence of that, 0. And again, a lifetime of 2. By the way, here's another thing that I can conclude from the lifetime being 2. Let's suppose we've got this already. I've got a vector field. I look at its curl. The curl is not 0. Let's speculate. Hey, I wonder, could this vector field be the gradient of some function? Answer, no, it can't, because if it did, we would have a lifetime of 3. Lifetimes can't be 3. Lifetimes are 2. Does that make sense? Okay. So all sorts of nice little theorems that you don't have to memorize by rote. You can just remember the pattern. Operators in this order, lifetimes are 2. It's pretty much as simple as that. So I think it's a great way to think about it. Again, these patterns emerge for deep reasons, and we won't be able to talk about that at all in this course. It's very sophisticated stuff, but at the same time, it's cool to know that the pattern holds. It's very convenient for understanding and remembering things to know that patterns hold, even if you don't know why patterns hold. Okay. All right. Oh, and let me real quick. I don't want to spend too much time on this, but constant functions are the sad counterexample. You take a constant function, you take its gradient, you get 0. That poor little fella only has a lifetime of 1. It's a sad story, right? But that's basically the only counterexample. And you got regularity issues. What if the function's not appropriately differentiable? Blah, blah, blah. Sure, but yes, those issues as well. But among nice functions, nice vector fields, this is the only counterexample. Okay. All right. So now we've done a bunch of stuff. I've talked about curl. I've talked about three-dimensional curl. I'm going to say everything we've done divergence. I'm going to say everything we've done has been in rectangular coordinates. Notice we're using rectangular standard basis vectors. Notice we are looking at the rectangular components of a vector field. When we write F1, F2, F3, we mean those are the coefficients in a linear combination of the rectangular standard basis vector. So all of this discussion has been rectangular. Let's try to switch it to polar. And it's just a little tedium. Ultimately, it's nothing to be afraid of. It is a lot of tedium. And I suppose there's a case to be made. You should be a little afraid of tedium because it's something that can eat up your time, and it's an opportunity to make mistakes, etc. But ultimately, it's just tedium. The big idea is we're going to take the objects that we're interested in, and starting with the most fundamental, we're just going to rewrite them in polar and plug them in and do what the formulas tell us to do. It's not that big a deal. It's just tedium. So, okay, here we go. These are old formulas that we've talked about long ago. I don't want to reproduce those discussions, but let me remind you, these, when we first introduced polar standard basis vectors, we wrote down either these formulas or analogous formulas. And all you got to do is just, you draw yourself a little picture, and ER points in the direction where R increases, and E theta points in the direction where theta increases, and you do a little geometry. It's not that big a deal. These formulas we wrote down when we were talking about the chain rule. And let me just remind you, if you have a function of x and y, well, x and y are functions of R and theta. You've got a composition. You do the chain rule, and you can write the R partial and the theta partial as functions or as expressions in terms of x and y partials. All I've done here is invert, right? I've solved for the x and y partials in terms of the R and theta partials. And we talked about this at the end of section 2.5. And we did at least one of these specifically. I don't remember. We might have done both. I'm sorry, I don't remember. But we've done at least one. So make sure to review, make sure to persuade yourself that you're comfortable with these formulas. And now, here's our del operator, rectangular del operator. We've got rectangular standard basis vectors, rectangular partial operators. We know how to write all of these in polar now. And again, we're just going to plug in. There's nothing too tricky about this. Solve for I. I ends up being that. Now, again, a little tedium, a little algebra. Make sure you can do that. Right? There's no way around the tedium. I'm sorry. But that's what I is. And you can likewise solve for J. And J is that. And let's see here. Partial with respect to X, we already have there. And partial with colors. Sorry. Partial with respect to Y, we have there. This is plugging in. Right? And then you look at this great big thing, and you can just multiply it out, collect terms, and there's cancellations and Pythagorean simplifications, and yada, yada, yada. Good exercise. Everyone should do this once in their lives. It's not hard. It's pretty straightforward. And what you find is that the del operator that we wrote like this in rectangular coordinates is this in polar coordinates. And this is very, very handy. Let me just remind you, why are polar coordinates and spherical coordinates handy? Because the world that we live in, the natural world that we live in, is full of round stuff. Right? So think about when you look out into the natural world, how often do you see rectangles? Not that often, is it? How often do you see round things? Oh, all the time. Planets are round. Atoms are basically round. Right? Certainly, potential functions, gravitational potential functions, for example, electric potential functions are radially. They depend on distance from the center. It's not natural to write that in terms of X, Y, and Z. It's natural to write it in terms of distances to points. So, when you find yourself doing real stuff, very often writing the functions in question in rectangular coordinates is weird and unnatural and strange. And oh my gosh, why would you do that? It makes so much more sense to write it down in polar coordinates. And if you've got it in polar coordinates, this is easy to work with. Right? So it's one of these, I've already shown you a different example of this, but it's, you look at your two options here. Do you prefer your rectangular del operator or your polar del operator? And a lot of people would say, I like rectangular. Oh, it's simpler. I like the pictures better. Certain things are constants. It's nice. This expression is shorter. This looks harder and curvier and weirder. And this is going to be a lot easier to work with in a great many cases. Is everybody with me? Does that seem believable? And I showed you the example with the Laplacian, right? And the rectangular Laplacian is no fun to deal with. The spherical Laplacian, snap. Very often the case. Okay. All right, we can keep going on this. Let's talk about a vector field. Now, here's how we have thought about vector fields previously. F1, F2, we're still in 2 dimensions. And these are rectangular components. These are the coefficients in a linear combination of rectangular standard basis vectors. Right? In particular, like so, right? You notice that these are literally coefficients of rectangular standard basis vectors. All right, well, very often it's much easier to write as linear combinations of polar standard basis vectors. And so these coefficients, aka these polar component functions, right? They're not the same as F1 and F2 up here, right? They're different. But very often, depending on the situation that you're looking at, they're much easier to write down FR and F theta. Because again, the world is full of circles and not so much with the rectangles, right? So very often this is just easier to write down in the first place. Don't think of it as how would you convert from this to this. Think of it as this is what you're going to have from the get-go. Is that cool? Everybody with me? All right, well, we know how to write del. This thing here is del dot F, right? All together, what I have here, that's just del dot F. I wrote del in polar coordinates. I wrote F in polar coordinates. Everything in sight is in polar coordinates. All this is a polar way of writing divergence, del dot F. And then you can dot it on out, right? And again, now there's a certain amount of plug and chug here. This one is very doable. It is a little tedious. It's definitely more trouble than this was. This is really actually very quick, right? This is a little bit more trouble. It is doable. And I think everyone should try to do this, to work this out and conclude this formula. That is the polar formula for divergence. And again, really handy. Great many circumstances. You don't want to bring rectangular coordinates in if there's no reason to use rectangular coordinates. Rectangular coordinates are often unnatural. So think of this as an alternative and in many cases better formula for divergence. How we doing? Everybody see the strategy? Many blanks to fill in. By the way, let me note as well, this, try it on your own. I think everyone should try it. It's a little tedious. You're going to notice stuff like, okay, at some point, this will be applied to that, and in particular, I'll be taking a theta partial of a product. And by the way, both of these are functions of theta. E theta, remember, is not a constant. E theta depends on where you are. E theta is a function of theta. So you're going to have to use the product rule. And it's annoying, and it's additional tedium. But if you just take a deep breath, slowly and carefully, be methodical in terms of how you write it down, it's just tedium, and it's ultimately not that bad. Again, you'll get down to this. If you have any trouble, I actually made this a test question last semester. In one of I had 2 sections. I had to do 2 different tests. It was a weird semester. But if you look at the section 7, exam 2, and I think it was one of the early questions. It might have been question 1. I don't remember. To be fair, it was a hard question. I graded it as a hard question. I curved it heavily, right? So it was fair, right? I didn't I didn't abuse those students, right? It's perfectly reasonable. But yeah, it's a lot to write down. But anyway, if you want to see, if you have trouble with this, right, check that solution, and you'll see exactly how that works. Okay. Let's see here real quick. You can do the same thing with curl. This is the polar curl. 2-dimensional polar curl. Again, nice handy little formula. By the way, all these formulas are on the internet all over the place. In fact, I think there's a Wikipedia page that has like all of the differential operators you'll ever need in all of the different coordinate systems you'll ever be using, and they're all written down in one handy spot, so you might want to find and record that page. Related, here is the spherical divergence. This one I do not recommend that you try on your own. This one is actually pretty tedious. It's not that it can't be done. It's just a little more trouble than I think it's worth. If you're looking for a challenge, right? If you're going to find yourself at some point with an hour or two to kill, and you want to give it a shot, go ahead. You can do it. It's ultimately not that different from what we just talked about. It's just more tedium. Okay. All right. It looks like we're out of time. Pretty good place to draw the line. See y'all later. Have a good weekend. See you on Friday. On Monday. See you on Monday. Sorry.